The A3000, the last ever BBC branded computer made by Acorn, and clearly a perfect fit for my end of the line series of videos where we talk about the last of a line of computers to be made. Except this machine's a bit tricky because it's kind of also not the end of the line as well either, it's more like the beginning of a new line, as many people believe that this is the first of the Archimedes lines of Acorn machines. Except it's not the first of the Archimedes machines because there are at least 2 other lines of machines before this one came out. In fact, this is just the first one you happen to be able to buy in a shop, and that Acorn, marketed to anyone. Which means that it's the first Archimedes machine that most people got to try and experience, and therefore they think of this one as the first because it was their first. So welcome to the end of the line for the BBC Micro / also not. Oh, this is going to be a complicated one. So before we get into the nitty-gritty and the excessively nerdy details about chipsets, I'm going to say that this video is sponsored by PCB, a fine purveyor of printed circuit boards. Yes, you design a thing, you upload the thing comes back in post. As the name would suggest, they are primarily focused on PCBs, but they also do CNC machining, injection molding, 3D printing. Still no news on knitting patterns though, sadly. So the big thing everyone knows about the A3000, or certainly did at the time, that it's based on the ARM processor. It's not the first machine Acorn shipped with the ARM processor. In fact, we have the 400 and 300 machines came out first, but this is the first time that normal people could lay their hands on a machine with an ARM chip in it. I mean, you could march down to Currys and, buy one of these things. And for people outside of the UK, Currys is a big electrical retailer. Now, the ARM processor was something that Acorn had designed in-house, as well as a number of support chips for the processor, like MEMc, VIDc, IOC. All of these would become core components of the Archimedes range of machines, including our A3000 here. Now, they'd refer to this as the 10x machine, a machine that would be 10 times more powerful than the original BBC Micro, while hitting the same price point. And okay, they didn't actually get there. The Archimedes is not 10 times more powerful than the BBC. It is a lot more powerful than the BBC, but they also didn't get anywhere near the price of a BBC. But there are a lot of very clever design decisions in the ARM processor itself and its supporting chips that help reduce the cost of this thing down significantly. What really kept the A3000's price above its contemporaries like the Amiga and the ST was just simply the likes of Commodore and Atari had better economies of scale because they were shipping more of these things. Acorn and the BBC's biggest presence was in the UK because that was their home market, but there were not enough machines being sold there to help drive down their costs. Now, one of the things everyone seems to know about the ARM is that it was a much faster processor than other contemporary processors in that space at the time. And I'm going to give you an idea as to how fast that is, because sometimes I think people exaggerate it a bit too much. So, for example, compared to a 68K clocked at the sort of speeds it was in the Amiga 500, it's about 7 to 8 times faster than that. We're about 3 or 4 times faster than, say, a 386 clocked at the typical frequencies it was at that time. And we're about, say, quarter of the speed of a Spark processor from this period, like a Sun 4. So compared to a lot of machines, particularly those in a similar price point, we were substantially faster than those, CPU-wise. But we're not quite up to what, say, a Spark workstation is, which, given those things started at like $20,000, that's not, super surprising. Now, admittedly, the likes of the Amiga had specialist graphics chips to kind of help make everything run at a decent speed, and the Archimedes range very much does not. We just have a straight frame buffer, basically, and a CPU to do all the work. Kind of like an Atari without the MIDI ports, but, a lot faster. Ooh, that's going to generate some comments. Before we get into the really nerdy detail of how this machine actually works and all the chips that are in it, we should probably talk a little bit about the BBC Micro itself. Now, for those of us of a certain age based in the UK, this computer is basically the ubiquitous machine that we used in all schools. And it ended up being so because of a competition that the BBC ran amongst computer manufacturers to get a computer that would match a particular spec that they were going to use as the basis of a program to educate school children about the use of computers. And to go along with that program, there was also quite a lot of government funding for schools to be able to purchase computers, where the government would cover half and the school would cover the other half. It wasn't just Acorn's machine that had access to this funding. In fact, schools could buy a variety of machines. It's just the BBC Micro was the one that the BBC was using in their programming and educational materials. So with all that material behind it, it kind of became the de facto standard for computing in schools. And by looking at it, you can see why. This is a fairly rugged, solid machine that can survive contact with a 5-year-old. Whereas the machine that they were planning on using for this, prior to it being an open competition, the New Brain, well, that's not going to survive 30 seconds of contact with a child who's one sherbet dib-dab away from committing a war crime. Now, it's while dominating this particular educational market that Acorn starts work on their new machine. Well, first the ARM processor, which they made available to software developers as a second CPU add-on for the BBC Micro, so they could prep stuff ready for their new machine, and then next they developed the chips that would support the ARM processor and make their actual computer. However, while Acorn's developing all of this, the world is not standing still. The IBM PC has come out, clone manufacturers are now a thing, and the PC's basically taken over the business world, at least in terms of micros. Commodore get the Amiga out in 1986, and Atari's managed to get their ST out as well. Apple have finally started to move away from the Apple II and have released the Mac, a home computer that costs somewhat less than the family car, unlike the Lisa, which is their first go-round at this. So by the time we get the first two Archimedes machines, and then onto the A3000, the world's somewhat more competitive than when Acorn started this thing out. So with the A3000, again, Acorn's turning to the BBC branding to help push and market this machine. As it's already an established machine, the BBC Micro, so they're hoping to build on top of that, particularly in the educational market with schools that already have a large software library of BBC applications and add-ons for the BBC. So how well does the A3000 do as a successor to the BBC Micro, a follow-on if you were? Because on the surface of it, you'd look at the spec and say, these two machines have very little in common apart from their manufacturer. The BBC Micro is an 8-bit machine with a 6502 processor and somewhere between 32 and 128k of RAM, and a whole bunch of proprietary ports for adding various add-ons to the BBC. The A3000, on the other hand, is a 32-bit microprocessor with 26-bit memory addressing and ships with 1 megabyte of memory. It also has its own proprietary Podule expansion system, but it doesn't come with any of the ports that the BBC Micro came with. Well, that's not entirely true. We're going to cycle back to that one. The operating system on the two machines is also pretty much completely different. Acorn had their text-based MOS for the BBC machines, and we have a GUI-based operating system, or at least that's how it appears to most people, known as RISC-OS for the Archimedes line, starting from the A3000 onwards. Before that it was called Arthur OS, but Acorn didn't want to call it Arthur 2 because there was a film called that coming out at the same time and they didn't fancy getting sued. Although, as we'll learn later on in the video, there's a lot more similarities between Acorn, MOSC and RISC-OS than you might first assume by just looking at its UI. So how does this machine fare as a BBC Micro? The answer is surprisingly well. Unlike every other manufacturer of 8-bit machines out there like Commodore and Atari, etc., Acorn included an emulator for the earlier system with their A3000. And while this emulator's not perfect, it is actually really good. You can run most software targeted at the BBC's hardware on this thing. There are some games that stepped around the BBC's operating system that did not behave overly well on the emulator, but for educational titles and applications, yeah, they pretty much all just ran fine. In fact, the emulator would also emulate some of the rarer hardware for the BBC, like a second processor. So assuming your BBC was using a 3.5-inch disc, you could just take that from your BBC, slap it in the A3000, start the emulator and run software off the disc. The emulator also had something known as HostFS, which let you access the RISC-OS machine's filing system inside the BBC emulator. If you had stuff written in BBC Basic that you wanted to run, well, you didn't even have to run the emulator because BBC Basic came built into your Archimedes. It had been extended somewhat so you could write GUI applications in it, but all your original BBC Basic code would run just fine. In fact, the Archimedes supports all the screen modes that the BBC did, so stuff that assumes that the screen mode works in a particular way, yeah, no, it just works. The emulator's really just there for machine code stuff. Other very important areas of compatibility that the A3000 had with the BBC is it supported Econet, Acorn's networking system. Now, at the time, this was a pretty big thing for the Archimedes because Econet was the most widely deployed LAN technology in the UK at that point and was in pretty much every school that had more than a handful of BBCs. So, being able to plug your A3000 straight into that network and access files off the file server, or in fact, use your A3000 as a file server to BBCs, well, that was extremely useful, although for a 32-bit machine that can handle up to 4 meg of RAM, Econet would be relatively slow, at least for loading software off. Not terribly slow, but software would noticeably take a little while to load. Whereas for a BBC Micro that has a usable 32k of RAM for programs, loading stuff off Econet seemed basically instantaneous. Furthermore, there were add-ons available to the A3000 that let it have some of the ports that the BBC Micro had, like the user port or the 1 MHz bus. And those ports were usable in the emulator, so if the school had invested in lab equipment, for example, that made use of that port on the BBC, well, you add the module, you connect it to the A3000, you use the emulator, and you're all good. When you're not wanting to run older 8-bit software, well, you have all the nice 32-bit software you can use now. Although there's not a lot of it around the release of the A3000, there is certainly some, and its software library will get a lot better. But compared to the PC, for example, there is a relatively low count of software titles. Although if you're a school, an awful lot of them are geared up to you. Also, for schools that had heavily invested in teaching programs for BBC Basic, well, that updated and improved version of Basic is just there, ready for you to use built into the machine. So schools can still make use of the same teaching and lesson plans they had previously, only now they can introduce concepts like the GUI into it. Now all of this is a good example of Acorn levering its position in the UK education sector that means there is a machine that's a good fit for what's already being done. However, it is pretty proprietary, and Acorn doesn't have much of a presence outside of the school market, so for some schools, while it let them keep using the software and things that they already had, it did mean that they couldn't teach new things that were more PC based, that schools were starting to feel would prepare children more for the wider world of business. So we do see the previous main presence in the UK education market, RM, stage a bit of a comeback with their IBM compatible-ish line of PCs, the RM Nimbus. And in schools, that is the main competition for Acorn's Archimedes-based machines. The home market has diverged somewhat, or at least in the UK, as PCs are far too expensive for home use, and while the Spectrum may be effectively dead now, Commodore has come in with its Amiga computer, which in 1989, the same launch year as the A3000, has the most successful sales period for their cost-reduced machine, the A500. And while Atari has slipped from being the most popular of the 16-bit platforms in Europe to number 2 behind the Amiga, it's still doing very well. And you will find it in the music departments of most UK schools. So, inside schools, the A3000 has some proper competition. Outside of schools, it also has some proper competition. Now, price is actually a pretty big deal here. So, by 1989, the price of an Amiga 500 had dropped to £399. The A3000, on the other hand, at least at its discounted price to schools, was selling for £529. At retail, that was £649. So even if you're a kid that really wanted the A3000, you were getting an Amiga 500 for Christmas. I mean, I was that child, and admittedly, I'm not that disappointed that I got an Amiga. Let's put it that way. I should probably also mention that £649, that's ex-VAT as well. So let's get this machine open and look at the nerdy detail inside. Now, there have been plenty of videos around that talk about the ARM and ARM architecture and how great that is and how it came to be, and completely ignore all the other chips that Acorn had to develop to make this thing go. So not only are we going to look at the ARM processor, we're also going to look at VIDc, MEMc and IOC. But we'll start with the CPU, which is an ARM2 clocked at 8 MHz. Now, this doesn't contain a lot of differences from the original ARM1 that Acorn shipped as an add-on to the BBC Micro for developing software for the ARM. And it's a pretty simple design because they wanted to keep the thing with sufficiently low power draw that they could package the thing in a plastic package rather than a ceramic one, because that would substantially reduce the cost of the individual chip. That would also fatefully lead to ARM's great advantages that would allow it to become the thing that it is now. Now, there is no onboard cache or cache management inside this CPU, which was a reasonably wise decision, because when you're designing your first chip, doing a CPU cache is, well, pretty challenging. Even now, cache coherency in a processor is not the easiest thing in the world to get right and test for. And at this point in time, memory is still available in similar speeds, clockwise, to a CPU. So an 8 MHz CPU could be paired with 8 MHz memory. So you could still get excellent performance out of your CPU with no cache. The other thing that they didn't particularly want to do with the ARM processor and all its subsystems was DMA, direct memory access. So they made the CPU particularly good at handling an interrupt, as they knew the CPU would be doing all the work of dealing with stuff from the I/O devices. This would also be where this 26-bit memory addressing thing would come from, because 26 bits is a really odd size for the pointer to memory, so you knew there had to be a good reason for it, right? Now you might be wondering, why not just do DMA? Other systems like the PC did DMA, and that comes down to this trying to keep it at a reasonable price thing, because DMA controllers were expensive. I mean, a lot of computers, the DMA controller costs the same as the CPU. So if you can have decent performance without doing DMA and shove all that functionality into the CPU, well, that's going to significantly keep your costs down. Another reason for not going for the cost of doing DMA is when your CPU has no cache. If you remember, I mentioned earlier that ARM2, there's no onboard cache on that CPU. So if you have to lock the CPU out of memory so hardware can do DMA, it's not like your CPU is going to be doing very much because it doesn't have a cache. So it'll just become stalled waiting on getting access to memory again. At which point you may as well just eschew the whole DMA thing and get the processor to do I/O instead. So that's what they did. And knowing that that was the plan when they designed the processor, well, they could design the processor to do I/O in software as fast as it possibly could. So in order to aim with that, the ARM processor had a fairly neat trick, referred to as the fast interrupt request. Now, when handling one of these fast interrupt requests, known as an FIQ for short, registers 8 to 14 of the CPU are banked, and when we're handling on these requests, we switch which bank is in use. So this means that if you write your interrupt handling code to only use registers 8 to 14, then your code can run without having to save anything in or out of those registers. And if you're not having to call either the load or store instructions very often, that means when running this code, your CPU doesn't have to go in or out of RAM and wait for RAM. And so our code can run very quickly. But this is also where the bit with the 26-bit addressing comes in, because register 15 is our program counter that stores the pointer to where we are executing stuff from RAM. And in any interrupt handler, you're going to have to save that value somewhere so you can write it back in and jump the code back to where it was supposed to be once you finish doing your interrupt handling. But those aren't the only bits of processor state you need to squirrel away and put back again. There are all sorts of flags that need to get stored as well. So here, Acorn came up with a fairly neat trick. What they do is they cram the program counter and all the flags into one register. So by the time we've used up all the bits to store the flags and CPU mode, interrupt mask, etc., we're left with 24 bits left for addressing. But I said before that it was a 26-bit addressing system, didn't I? Well, that program counter is 32-bit word aligned, so that effectively gives us a 26-bit addressing system. Now with the PC and the entire CPU state all in one register, that means you have one register to save, at the cost of limiting yourself to 64 megs of address space, which in 1986 was an awful lot of address space. So no one felt like this was a major restriction on the platform. And if we'd ended up having a full 32-bit program counter and then another register for the status flags, well, every time you handle an interrupt, you've got twice the work to do, 2 registers to write out and pull back instead of 1. So this is an incredibly sensible trade-off for this point in time. I mean, eventually ARM would move to using a 32-bit program counter because 64 megs of addressable memory becomes somewhat of an issue later on. But at this point in time, 64 meg of memory is way more memory than anyone is going to stick in one of these machines. I mean, remember, Acorn's got this thing initially strapped up to a 32K BBC Micro while they're developing this stuff. So a 64 meg address space seems pretty flippin' huge. And from a risk point of view, it's also really nice because you don't have to have a separate instruction to return from interrupt. You can do a subtract into PC to jump back to the right point. Now we've talked about how FIQ works with the CPU, let's have a look at IOC, the chip that's designed to handle the I/O. Now we've already established that it does not do DMA. So what does it do? Well, for a start, it handles all the cycle timings and glue logic for all the various I/O inputs that come into the system. Those 16-bit modules and that 8-bit Ethernet slot. It also has a little serial UART in there and microcontroller that handles all the keyboard and mouse input. So our processor does not have to handle all the keyboard scanning stuff with row and column. Our little microcontroller in IOC just gets on with looking after the keyboard. We also have a series of 4 2MHz timer/counters that various software applications can make use of. It also handles all our GPIO and I2C stuff as well. It also stores all our interrupt masks, etc., and the interrupts from all our devices end up getting marshalled there before it flags up an interrupt to the processor. The next chip we're going to talk about is MEMc. Now, there's a lot going on in MEMc, but it's basically responsible for controlling and managing all the memory in the system and getting the CPU in and out of it. It also has a pretty special function related to the video chip as well, which we'll come to later. Now, one thing that might surprise you about a chip that's designed to manage what's happening with memory is that it only lives on the address bus and not on the data bus. Now, you might think that's a pretty odd choice that Acorn made there, but they did have their reasons. If you need to put your chip in a package that had enough pins to be able to do both the data and the address bus, well, that was a lot more expensive package. So if Acorn could get away with just putting this thing on one bus, well, that'd make this individual chip a lot cheaper to make. They also repeat this, but it's just on one bus trick with a number of the other chips as well, always conscious about how packaging can really push up the price of a chip. So this chip provides some features that you might at first thought not occur to you that's going to be here. So clock generation is one of the things that this chip does. And that allows it to control when the CPU is getting in and out of memory by essentially stalling the processor for a little while with the clock signal. Now, you might wonder, in a system with no DMA, why on earth you'd want to stall the CPU from talking to memory. And that's because I sort of lied to you. The vast majority of our hardware has no DMA access. The video chip, however, VIDc, sort of does DMA. And as I mentioned before, this chip has some special features to do stuff with the video, and I will come back to this later on, but this is around this whole DMA sort of idea. So that's why it's useful that clock generation is done inside MEMc. Also, we have to stick it somewhere, right? Unsurprisingly, this thing does the refresh of the DRAMs, so stuff keeps being in memory, and it also does the translation from the address to the row and column system that DRAM chips use for addressing. Now, one of the interesting bits, by the time we've got RAM to doing this, we've hit the point where accessing every byte in RAM does not happen at the same speed. If you're doing a read or write to memory, waking up the first cell in a block takes longer than all the subsequent linear reads or writes that happen after that. And this is why the ARM chip breaks the RISC rules a little bit and has store and read multiple, where it'll read or write multiple registers at once to memory, rather than just calling the one load or store instruction multiple times. It does have a single register read or write instruction, but the more we make use of the read or write multiple, the higher utilization of the memory bandwidth we make. This is actually a big part of why the ARM processor is quite so fast, as other competing CPU architectures at the time didn't really make use of memory bandwidth in quite the same way that the ARM did. Now, the other thing MEMc's got, and it takes up nearly half the die in this chip, that's more or less the same size as the ARM CPU itself, is it's the MMU. Now, even around this time, you're getting CPUs that have the MMU built in if they've got one. But again, this goes to cost. If you try to get the MMU inside the ARM chip, well, it would have needed about 50% extra die space. And as each time you increase the size of the die, the yield falls off. The ARM chip already had a die that was the size that was the most economically viable at the time. So it was definitely going to be cheaper to not have the MMU on the ARM chip itself, but have it in MEMc. Now, MEMc is also where one of the big restrictions in the whole Archimedes platform comes from, the whole 4 megabyte physical RAM limit. Or at least 4 megabytes per MEMc chip. You could have more than one MEMc chip in a machine. But the likes of the A3000, being a more budget-conscious machine, at least for Acorn, only had one MEMc chip on the board. That's why the A3000 maxes out at 4 megabytes of memory. The bigger pizza box and desktop machines, some of those would have a MEMc chip on the RAM upgrade card they made use of. And for each one of those MEMc chips, they could have 4 mega physical RAM, all the way up to the limit of 16 megabytes. As physical memory can only use up half the address space, because virtual memory takes the other half, and a bunch of that address space is taken up with ROMs, and also the memory address space for I/O devices, leaving us with 16. Anyway, back to the MMU. Now, this particular MMU works backwards from the way that most MMUs do, or at least I'm pretty sure that it does. There's a lot of documentation that says it goes from physical address to flagging which page in virtual memory that physical address belongs to, rather than us trying to map a virtual address to a physical address. It works backwards, effectively. At least that's what all the documentation seems to say, unless I've horrifically misunderstood it. Now, I honestly can't work out why this was their design decision. I assume it was cost-based. It's just I haven't figured out what makes this design massively cheaper than doing it the usual way round. But this design is also where we get our 4 megabyte limit from, because the chip is essentially cutting the physical memory up into virtual pages. Now, the MMU provides 128 physical pages, and that is limited by essentially the size on die you have for this page table. Now, it doesn't matter how much memory it's controlling, there's always 128 pages, So the size of a page varies with the amount of memory, not the number of pages. That also means there can only be one virtual mapping to each physical page of memory, and with MEMc only being on the address bus means it only does address translation, it doesn't do any I/O remapping. Now, with a fixed number of pages and variable page size, it turns out there really is a maximum size you want your page to be for it to still be useful, and that's round about 32K. So 128 32K pages gives us this 4 meg of physical memory limit per MEMc. Obviously, if we added a second MEMc, well, then we have 256 pages of memory. And 256 pages of memory at 32K maximum size, well, that gives us 8 meg of memory. And so on and so forth with each MEMc that we add to the system and 4 megs of RAM. Now, you might be wondering to yourself, with it only being on the address bus, how on earth do we set up the page entries in the MMU? Because we can't write data to it. Well, here the design of MEMc is fairly smart. How it works is, there are a number of addresses that are reserved for controlling MEMc, or a MEMc, and we get the CPU to set that particular address, and then it writes any value out. It doesn't matter what the value is, only that it writes. The MEMc lives on the address bus, so it gets to see the address that's been selected, and it gets to see that the write line has been hit. With MEMc not being on the data bus, it doesn't actually get to see the value that the CPU writes out, but that doesn't matter, it's just decoding this address data. And it uses that address data to work out what entry you intended to put in its little page table. Now, having a block of address space that can only be written to would be a little bit of a waste, but if we look at the Archimedes memory map, we can see right at the top of that address space, in the section that's only accessible when the chip's in supervisor mode, you can see we have the ROMs for the operating system, RISC OS. And the control for MEMc has an 8 megabyte area that it overlaps with the 12 megabytes of ROM space. If you read from something in that 8 megabyte range, you get what's stored in the ROM. If you write to it, then you write to the control registers of MEMc. This is a pretty smart way of not wasting a bunch of address space, because ROMs can only be read, there's nothing you can write to them, because they're ROMs, and the MEMc will only take values that are written to it, there's nothing to read. So this system of overlapping saves us some valuable address space. After all, we only have 64 megabytes of it. You can also see in this memory map that we only have 16 megabytes allocated for physical RAM. And that's because we've got to have a mirror of the physical address space in the virtual address space, so physical gets 32 megabytes of address space and virtual gets 32 megabytes of address space. We're then using our top 12 megabytes for our ROM space, we're then using the next 4 megabytes for our I/O space. After all, your hardware has to map somewhere with its buffers, little bits of memory and the ROMs that are on there. And that 4 meg range is where it happens. And after that, well, that leaves us 16 megabytes of address space, hence the 16 megabyte limit in this particular architecture. With later Archimedes machines, like the RISC PC for example, assuming you count that as part of the Archimedes range, well then you've got 32-bit addressing and we can have a much bigger address space and memory map, but thus we can have a lot more physical RAM in a machine. This 16 meg limit might feel like it's quite a big problem, but it's really not in 1989, as then 16 megabytes of memory is still a huge amount of RAM. For example, the entire Amiga 500 and 2000, etc., that can only physically address 16 megabytes of RAM, and barely any of those machines ever held 16 megabytes of RAM. Some machines, for example like the original Mac, while it may have had a 16 megabyte addressing limit in terms of what the processor could do, you still couldn't stick 16 megabytes of RAM in it. In fact, 16 megabytes of RAM would have been about 4 times as much as a pretty well-spec'd PC had at the time. In fact, plenty of PCs at the time didn't have the physical slots to install more memory than 4 meg, or sometimes in the nicer ones, 8 meg. So there's one major chip left, VIDc, which unsurprisingly is the chip that handles video, and also audio. Most people seem to forget to mention the audio part. For the time period, VIDc is a surprisingly capable graphics chip. You can have colour depths of 1-bit, 2-bit, 4-bit, or impressively 8 bits per pixel. And that gives us a maximum of 256 colours on the screen at once. And if we compare this to other machines around the same price point, well, more or less, like the Amiga for example, which is a machine very much thought of as graphically capable, without doing clever tricks, that's essentially limited to doing 64 colours on the screen at once, and even that's an extra half-bright mode where you have 32 colours, and then the other 32 colours are just half-bright versions of those original 32 colours. Like the Amiga though, VIDc also pulls from a 12-bit colour palette, which means of the however many colours you're currently displaying on once, that draws from a palette of 4096 colours. However, unlike the Amiga's display, this is essentially a process-driven frame buffer. Almost, we'll come on to how that actually works later on. But you don't have the blitter, you don't really have hardware sprites either. Well, you do, you have one, which is used for the mouse pointer. There's also no fancy planar modes or anything like that, so this is all done as chunky pixels, where essentially you write the colour you want to be in a particular pixel into a location in memory. But this is a lot better for doing 3D stuff than the planar mode. That's all about essentially fast moving sprites, which we don't have any. Well, we have one. It does also have the concept of transparency built in, so this makes gen locking the output of the ARC pretty easy actually. There are also some cheaty display tricks like there are in the Amiga, so although you can't quite do hold and modified the way it did to get 4096 colours on the screen at once, you kinda can with those programmable 20 MHz timers we talked about in IOC. You also had a reasonable range of screen resolutions as well you could get VIDc to output, so you could do 1024 by 1024 in monochrome, all the way down to 640 by 265 in 256 colours. Now I should also cycle back to the audio, because I did say that a lot of videos ignore the audio when it comes to VIDc, and this very much is the sound chip as well. And it supports 8 stereo channels in 8-bit, but that's a logarithmic 8-bit, so this actually sounds better than you would think. In fact, if you should compare it to non-logarithmic systems, it sounds more like it's a 12-bit audio stream. If you're familiar with PCM audio, it's basically like that. Now, interestingly, putting the audio and video in the same chip, at least for VIDc, the original version, did actually cause a little bit of interference. There was noise on the video output signal created by the audio signal, at least in VIDc 1. In VIDc 1A, they did actually fix this in quite an interesting way. They took the audio signal, inverted it, and fed it back into the video signal, so the inverted audio signal would cancel out the noise from the audio signal, thus giving you a clean video signal again. I must admit, I love the beauty of this as a solution. It's basically noise cancelling headphones for your video signal. Now VIDc, kinda like MEMc, only sits on one bus. It only sits on the data bus, not the address bus. And again, this keeps the pin count down on the package that VIDc is packaged in, thus keeping its cost down. Now you might be wondering, so how does VIDc select which bit of memory to read so it can output its video signal? And the answer is, it doesn't. MEMc does. This is where we come back to that whole sort of DMA thing I talked about with MEMc and VIDc. So VIDc itself just has a FIFO in it, and MEMc essentially streams data along the data bus without actually being on it into that FIFO. And VIDc basically takes what ends up in his FIFO, squirts it out through its digital to analog conversion process, and there's your video signal. Okay, the practicalities of that are a tiny bit more complicated, but that gives you a good overview of the actual architecture that's underlying this. So MEMc holds a number of registers, like where in memory does the video frame buffer start, where are we currently in the video frame buffer, and how long is the frame buffer. Now remember, MEMc's only on the address bus, so it can hold the addresses for us, and VIDc is only on the data bus, so there's no point in it holding addresses because it doesn't have access to the address bus. So there are a couple of lines that run between VIDc and MEMc to do a bit of a handshake. So when VIDc's essentially knows its FIFO starting to get towards empty, it exchanges a message with VIDc to say, send me some more data. MEMc, because it does the clock generation for the CPU, can now stall out the CPU to stop it from reading from the data bus, and because it has a register for where the frame buffer starts, how long the frame buffer is, and where the current position in the frame buffer is, can calculate out the address in memory that VIDc needs to start receiving data from, and it passes those addresses into the DRAM, which outputs that content onto the data bus. At the same time, it sends an acknowledge signal to VIDc to tell it to start reading and shifting whatever's in the data bus into its FIFO. Once it's moved that little chunk, MEMc can stop inhibiting the clock to the CPU and start sending it its normal clock cycle, and the CPU can just get on with its life, until the next time VIDc happens to need more data, at which point we go round this little cycle again. Sound basically works the same way as well, the only difference being there's a double buffering scheme going on here, so when half the buffer's been got through, it generates that little interrupt that gets it to shove and fill that sound buffer back up again. Now, this is a really neat system for getting most of the advantage of DMA for your audio and video, without doing all the sorts of things that other systems that do DMA have to do. And for a machine designed to be essentially a personal workstation/desktop computer, this is a perfectly decent arrangement. We're not being a server, we don't care how fast we shuffle things from the hard disk to the network card, for example. Or at least in terms of compared to keeping video alive. So programmed I/O through the CPU for anything that isn't graphics and sound is still pretty performant, just without pushing up the cost of the machine by having to acquire a lot of complicated DMA components, while still getting us a lot of the advantage of regular DMA for our video and audio. All whilst keeping the pin counts down on all the different packages to make them all much more cost effective to manufacture. So how does our A3000 stack up to the competition? Well, it kind of depends on which market you're talking about. In the educational school space, it has the advantage that it is a very good follow-on to the BBC Micro, compatible with a lot of BBC Micro based stuff that schools already have. However, in the UK at least, the curriculum is changing somewhat. It's becoming much less based around what you think of as computer science, doing software development, etc., and learning how computers work, and much more about, let's learn to use a spreadsheet. Yes, it got very business IT focused, and they wanted to train kids to be able to use a spreadsheet and a word processing program, and ideally the ones that businesses were using, on PCs. So that got RM and their Nimbus line solidly into schools. Now previously RM had been a big supplier of machines for educational use until the BBC Micro became a thing, at which point their share of the market kind of plummeted somewhat. But they have a line of sort of IBM compatible-ish machines. I mean, they're not really true PCs, but they can supply you a modified version of DOS that will work on it, and a modified version of Windows that will work on it, and some wrappers that will allow other applications that run under DOS to work. I mean, once you add the modified Windows applications, those tended to work just straight out of the box. They also provided some compatibility layers to try and get some stuff that wouldn't just work in DOS working, and while the RM Nimbus graphically is a little bit better than most PCs of the time, it's still nowhere near as capable as the Archimedes line is, particularly the A3000. Processor-wise, they shipped it with a 186, so again, the A3000 kind of trounces that fairly easily. I mean, by a really massive margin, actually. And when it comes to sound, the RM Nimbus doesn't have any. Networking-wise, the Archimedes can go onto an Ethernet network that your school probably already has with all its BBCs, whereas the RM Nimbus, it does come with ZNet, which is its own fairly cheap system for networking the Nimbuses together, and actually data rate-wise, they're very similar to each other. They even have a very similar addressing scheme of an 8-bit station number, although I'm not sure if ZNet also had a network number as well. So I don't think you could link multiple ZNet networks together. I may be slightly wrong about that. But all in all, if you compare the A3000 versus a Nimbus 186, the 3000 is a better machine. It's just not a PC. And with the change in curriculum to let's do word processing and Excel, you were starting to need to be a PC. Now, you can probably tell that I don't think that was a particularly good change in the curriculum, and well, it turns out these days most schools and the people who set the curriculum agree with me, and it shifted a lot more back to a more computer sciencey kind of a curriculum. The assumption is kids can just pick up learning to use a word processor and an Excel spreadsheet as they need to in other subject areas. And you know what, it turned out they could. In the home market, the leading system it was stood against was that of the Amiga, or the Amiga 500 in particular. Sorry Atari users, I know the ST was out there, but there's a limit to the number of machines I can compare this thing to at once. So we'll pick the leading system in the UK market, which is where the A3000 was mostly sold. So the Amiga 500 was a lot cheaper than the A3000. There's a couple of £100 in it. But at least in terms of processor, it is significantly more powerful. Compared to a 68K clocked at say 7 MHz, which is what the A500 has, it's about 7 times faster. But the Amiga does have a lot of custom graphics chips. So for example, it's able to do a lot of hardware sprites, so you can move around bits of the screen purely in the graphics hardware without the CPU really having to get involved apart from laying some instructions down for the graphics chip. You also have the Blitzer, which again writes a lot of screen memory all at once and can do all sorts of interesting little effects. And we've got hardware scrolling as well for the screen. So you might think that that adds up to games on the Amiga running a lot better. I mean, for those games that were ported to both the Amiga and the Atari, where the Atari didn't have the same level of graphics hardware, the Amiga version would typically have more things on screen, scroll more smoothly, particularly the backgrounds, and that's down to all that custom graphics hardware that's in the Amiga. So when we get games ported to the Arc, where we have an Atari and Amiga version, we'd probably expect them to behave a bit more like the Atari. But no, they tend to look and move a lot more like the Amiga version, because that processor is 7 times faster. That gives us more than enough CPU resource to move the same amount of stuff around on screen in the same sort of way, or at least visually, as the Amiga does. We also tend to sound a lot more like the Amiga version, because it tended to use sort of sound based on sample playback, even for the music. And again, our A3000, it can do exactly the same thing. It can actually do it in something that sounds ever so slightly better and has more channels, but most game software houses are not re-recording and doing all their audio again for the Archimedes. Where the Arc gets to really shine over both the Amiga, and in fact the ST, is with 3D graphics. Not having to do everything in planar modes makes writing stuff into memory from the kind of raycasting calculations you use a lot faster. The Amiga also doesn't have much in the way of special graphics hardware to really help with the whole 3D thing, so it has to just fall back to what the 68K can do, and the 68K can do about 7 times less stuff than the Archimedes processor can. So hence you get some 3D titles that start life on the Archimedes and the A3000 that look, well, really good. So you have David Braben's Zarch, which starts off as the Lander demo, and eventually we do end up with a version of that on the Amiga called Virus. It is one of the standout titles though for the Archimedes platform, as well as its version of Elite, Arc Elite, which for many years was basically the best version of Elite out there. Also a pretty much standout game for the platform was Conqueror, a 3D tank battle game created by Jonathan Griffiths, the guy who did Snapper for the BBC and Acorn Electron. He apparently used part of the landscape drawing engine that David Braben had created for Zarch, or Virus, used that to do the terrain and created essentially a really good tank battle game. This is what we tended to run on our school's Archimedes machines when the CDT teachers weren't looking, and it was one of my favourite games on the whole Archimedes platform. Now that's not to say there weren't a ton of really good games ported to the Arc. In fact, most of the ones you think of as, wow, that's a really good game on the Amiga or the ST, yeah, there's an Archimedes version of it. It may have come out like a year or two later than the version on the Amiga or the ST, but it did eventually get them. So there was no shortage of games for the platform. And sometimes the Archimedes version of the game would actually be better than the Amiga or the ST version, but not very often. A lot of it was kind of shovelware from other platforms onto the Arc. Which is a shame, because with all that extra processing power and 2 meg of RAM as standard, you could have really made some significant improvements to a number of these games, at least graphically and sound-wise. And also it could just display more colours at screen at once than the A600 and 500. It wouldn't be until the Amiga 1200 that the Amiga finally got a 256 colour mode. So how well did the last ever model to bear the name BBC on it sell? While being squeezed by cheaper machines at home and the PC coming into schools, it still sold reasonably well enough for Acorn to make a number of sequel machines. In the wedge form factor that the A3000's in, we see that Acorn releases the A3020, which is the top-end, more school-focused version, and the A3010, which is aimed much more at the home user and is a bit more budget. Now, these machines were somewhat more performant than the A3000, about 50% faster. And that's a couple of things working together. Firstly, there's faster RAM in there. They've also managed to clock the processor up to 12 MHz, but also this contains an ARM 250, which is the ARM-free instruction set, but with no onboard cache, but all the other chips that make up the Archimedes, IOC, VIDc, MEMc, etc., all in the same package. This is effectively a system on chip. Now again, this is very cost effective, but also all that tight on-die coupling means that things can clock up faster. At the higher end, we see Acorn releasing the A5000 to replace some of their more expensive machines, and then we'll also see a laptop version of this in the form of the A4. After that, we would then see the RISC PC line of machines and the A7000. Now you will hear people referring to the RISC PC and the A7000 as Archimedes machines, and formally, actually they're not. Acorn referred to their RISC PC line as a replacement for the Archimedes line, and they are actually architectured a bit differently. There is still an ARM processor at the core of these things. There's a chip known as VIDc20, that's the display controller effectively, but you won't find a separate MEMc chip or IOC chip because those functionalities have sort of been taken into the ARM CPU now, and they just don't work the same way. You don't have the same memory restrictions. In fact, this RISC PC you can see here, it's got 256 meg of memory on board, which was a lot for the time. In fact, I doubt many people at the time had that much memory. It's just you can stick this much memory in, and that's quite cheap to do now, so I did. We sadly also no longer have something on board to let us put an Ethernet interface in, so I've had to add a module that does that. And also I have an IDE module as well, so I can sit these little disk modules on and use them instead of spinning glass, because who needs spinning glass hard drives in their life anymore for their retro machines, particularly 30-year-old spinning glass hard drives. This thing also has a strong ARM processor in it, which is a processor not designed by ARM, but by DEC, the Digital Equipment Corporation, who licensed the instruction set off ARM, but did all the chip design themselves, and at the time gave us the most powerful ARM chip available. Unfortunately, it can't really be used to its full potential in the RISC PC, because there's not quite enough bandwidth in and out of RAM. But it was still a hair chunk faster than the processor that the machine originally shipped with. The RISC PC line runs RISC OS, just like the original Archimedes machines, but we can't necessarily run all the software we ran before, particularly if you happen to have a strong ARM, as it doesn't support the then legacy 26-bit addressing. However, some clever people did create a software layer that allows it to do, or at least sorts out the 26-bit addressing issue, so older software, particularly games, can run. Sometimes a bit too fast, though. As well as the special module slots, we do actually have a special network slot for an Ethernet card to go in. Yes, we finally moved on to the world of Ethernet, because an Ethernet card now doesn't cost more than the computer it's going in. But other networking systems like SJ's Nexus, which was cheaper to purchase, also could make use of that slot. But as a sign of the times, you'll see in its second processor slot, I essentially have a PC on a card. Well, or at least a PC processor on a card. And with that, I could boot up an entire PC in here and run DOS or Windows 95 on it. This did mean that RISC PC owners could run DOS or even Windows 95, and some even ran Linux on this thing. Although Linux would get a direct port that you could just run on the RISC PC itself. And while this did broaden up the software that a RISC PC owner could use, I do fear that it maybe hastened the migration off the RISC PC platform for a number of people. And this is where Acorn's line of computers actually genuinely comes to an end. After this, there are no more computers from Acorn. They did start prototyping out the RISC PC 2, of which many of us have seen the case for because those all got sold off. There is apparently still at least one prototype kicking around at the Centre for Computer History. But sadly, the RISC PC would be, well, the end of the line for all things Acorn and computing. Its processor, the ARM, though, that would go on to have, well, commercial success beyond the wildest dreams that Acorn could have ever imagined. In fact, based on the metadata I get from viewers, more of you watch these videos on an ARM-based device than anything else, because they power your phones, your TVs, your tablets, Chromebooks, even Macs now. Yes, someone is making an ARM-based computer these days, and it's Apple. Well, if you got to this point, I'd like to say thank you very much for watching. I would also like to thank Dudley of Yesterday for the cannon fodder footage, a phrase that turned out to be slightly more of a tongue twister than I was expecting. Cannon fodder You don't know how many takes I did of that. But I'm also going to mention him in a new section, Further Viewing. Because in an entirely unplanned move, despite the fact that I actually did a little bit of voiceover work for it, this month's Yesterzine is Acorn user, and is about the right period that we've been discussing here. So if you want to see some of the magazine coverage of these Archimedes machines from the period, then go have a look at that. You can also see some of the stuff that would have come on its cover floppy disk too. If you've not already, followed the link in the description to go watch Yesterzine, and you enjoyed this video, YouTube have provided a button you can use to indicate that fact. If you didn't, there is also another button, and we'll just say thank you for the engagement. If you really like the video, well then there's a subscribe button that will subscribe you to the channel, and that really helps the algorithm tell people that these videos exist.